we started to explore the goal of substantially reducing particulate air pollution in Asian cities by 2030 from the perspective of Adaro, an Indonesian coal mining and energy group. Adaro is the largest supplier of coal in the domestic Indonesian market and sold a total of 57 million tons of coal in 2014, with Asia accounting for circa 90% of these sales. While Adaro's main business is and always has been coal mining, they have recently implemented a strategy of moving into power generation. In line with Indonesia's goal of installing an additional 35 gigawatt in electricity generation capability over the next 5 years, Adaro aims to install 20 gigawatt of generating capacity by 2030. This strategy creates demand for Adaro's own coal, secures them a stable revenue stream, and hence minimizes the impact of volatility in the coal sector's cyclical nature. Coal-based power plants have a larger dominance in Asia in comparison to Europe or the US. As a percentage of the installed capacity in each region, coal-powered plants account for 62% of all plants in China as opposed to 26% in the European Union. China's 12th five-year plan from 2011 to 2015 explicitly called for the retirement of small, aging and inefficient coal plants. The plan introduced a national carbon trading scheme after 2020, while in 2011, 6 provinces and cities were given a mandate to pilot test a carbon pricing system that was scheduled to be launched as early as 2013. Regulations had become stringent where PM 2.5 emission from new plants after 2012 could not exceed 20 mg per normal cubic meter. The regulations imposed on existing plants soon followed after 2014. The European Union, on the other hand, had more strict regulations on PM 2.5 emission prior to 2012 at 15 mg per normal cubic meter. According to the regulatory report by the International Energy Agency, new regulations imposed until 2020 included maximum PM 2.5 emission of 10 mg per normal cubic meter. The report also expects regulations in both regions to be tighter after 2020. The regulations imposed will cap PM 2.5 emissions to a maximum of 5 mg per normal cubic meter. This video will focus on 3 key technologies including Pristine M, circulating fluidized bed, and the electrostatic precipitators. We can classify coal upon its stability and quality. The unstable coal emits large quantities of particulate matter in the air during transportation. The specific type of particulate matter released is known as PM 2.5. That are transported to long distances and suspended in the air for a prolonged amount of time. Therefore, to meet the future regulations, the particulate matters could be reduced at this stage by making the core more stable. Regulations around the world are getting more stringent, and we can assume that most countries will ban the use of low-rank coal due to its instability and high pollutant characteristics. China, which accounts for 45% of global coal consumption, have banned imports of low-rank coals with ash content higher than 16%, sulfur content higher than 1%, and particulate matters above 20 mg per normal cubic meter. Having a higher ranked stable coal will enable Adaro to keep exporting sustainable energy to use. With the research of technologies and coal and clean, we ended up with a certain amount of companies interested about this subject. What we realized with this quid was that the company that is the most shared on social media was Clean Coal Technologies, represented by yellow and blue on the snapshot. By looking closer to this company, we found one of its newest technology, Pristine M. The technology, just tested last August and validated in October, upgrades low and medium rank coal into premium fuel. Pristine M extracts the volatiles and moisture from coal in a liquid form and then coat the coal with it. This fills in the pores and makes the coal being stable and good for transport. It removes moisture from 50% to 10% and improves the calorific content to 6,500 kilocalories, as well as lowering the pollutants and increasing its efficiency when burnt. So how about the cost efficiency of this technology? As we can see on the table, this technology doesn't only help reduce PM by creating a stable coal, but also multiplies the market price of coal by 2.5 times. The table also illustrates the cost of the technology in electricity, labor, and maintenance, as well as capital costs. Indeed, this technology has an expected life of 20 years for a price of $2.50 per ton. Pristine M will enable us to have a stable coal for good transport use and meet the future regulations. HELE technology stands for High Efficiency, Low Emissions Coal Technologies. They incorporate measures to raise both plant efficiencies and reduce non-GHG emissions. The Quid article search with the query HELE and coal shows an exponential increase in the industry's interest from October 2014 to present. Since June 2015, there has been a substantial growth in interest on HELE technologies from Asia compared to any other regions in the world. PCC boilers had maintained a dominant role in coal power generation since the early 20th century. However, more recent boiler technologies had been developed to replace the original PC-powered plants. The two main technologies are IGCC and CFBC. We have decided to focus on CFBC technology due to their similarity to the original PC units and its access to economical retrofit of aged PC boilers with the relatively new CFB technologies. The internal recirculation CFB technology has become a viable long-term solution for upgrading power plants and extending the plant life for another 20 to 25 years. So what is CFBC? CFBC is a process of recycling fuel and limestone particles to result in high efficiencies for burning fuel, capturing pollutants, and transferring heat energy into steam. In step 1, fuel and limestone are fed into the combustion chamber while air is blown into fluidized mixture. Step 2, heat from the combustion process boils the water in the water tubes, turning it into high energy steam. Ammonia is injected to further reduce nitrogen oxide emissions. Step 3, returns ash and unburned fuel to the combustion chamber for reburning. Step 4, lime is injected into the polishing scrubber to capture more sulfur dioxide, while a particular control device known as the bathhouse collects dust particles. Step 5, high pressure steam spins the turbine, which converts mechanical energy into electricity, and the last step, it is delivered to distribution systems. CFB's rate of heat energy transfer can be as low as 60% of the conventional PC units. And CFB furnace tubes do not experience a significant rise in tube temperature, even at dryout, because of the low heat fluxes. An example of a CFB power plant is the 460 megawatt electrical plant in Legnica, Poland. Commissioned in June 2009, it is the world's first CFB technology with vertical tube, 1/3 unit, supercritical steam technology. The implementation of CFB technologies have increased plant efficiency from 35% to 44% while reducing nitrogen oxide emissions by 71% and carbon dioxide emissions by 28%. The following is a case analysis when running a 600 megawatt net CFB supercritical plant operating at 90% capacity factor. There is a reduction in capex due to less equipment required, but there is a potential arbitrage of $14.6 million per year fuel savings and a 10-year NPV fuel arbitrage of $95 million. The global trend is moving towards carbon capture and storage incorporated with HELE technology to meet the more demanding regulation targets. China's 12th five-year plan capped coal production at 3.9 billion tons by 2015, while imposing all plants of 600 megawatt or higher must incorporate supercritical or ultra-supercritical technology. Hence, the carbon intensity targeted by 2015 has been reduced by 17% and is expected to reduce by 40 to 45% by 2020. The following roadmap identifies technology implementations to meet the rising regulatory standards in major Asian countries. By 2025, with the deploy of ultra-supercritical CFBCs, non-GHG emissions will meet the standards of less than 50 for SO2, 200 for NOx, and 50 mg per cubic meter for PM. This number will be further reduced by 2030 with the introduction of advanced ultra-supercritical CFB boilers. This pattern search on ESP demonstrates that from 2010 onwards, there has been an increasing number of relevant patents filed from China. This is probably due to harsher regulations set in 2012 and 14 as outlined earlier. Particulate control and dedusting is required as flue gases created by the coal-fired combustion processes are loaded with PM and require cleaning before their release into the atmosphere. Dedusting devices enable this, and a continuous monitoring of dust concentration is needed in order to comply with the regulations. ESP is a device that employs electric fields to separate particles from gas streams onto collector plates from where they can be removed. Particulate removal efficiency is 99.7% and higher. The performance characteristics depend on electrical resistivity and particle size distribution, as well as gas conditions and gas temperature. Improvements are required to comply to the regulations from 2010 to 2020, and therefore, to achieve less than 50 mg per normal cubic meter of outlet emission, the following actions can be adopted. First, injection of one or more of the following upstream of the precipitator: sulfur trioxide, ammonia, or water. And second, gas conditioning. We can observe on the table that for emissions of PM equal to 50 mg per normal cubic meter, ESPs are more cost effective than fabric filter, another dedusting technology. However, reducing the emissions demonstrates a new situation in which fabric filters appear to be more cost effective than ESPs. Hence, we need to consider other performance improvements for years to come to overcome the need for fabric filters. The main difference between wet and dry ESPs is the use of a pre-quench and the collector plate cleaning method. Wet ESPs make no dust entertainment and is not affected by dust resistivity. They seem like a good fit to comply to stronger regulations that are predicted to be implemented in China between 2020 and 2030. China could aggressively reduce PM emissions to as low as 1 mg per normal cubic meter, and this could possibly be extended to other countries. Many power plants are currently equipped with dry ESPs, followed by wet FGD systems for PM and sulfur dioxide control. Wet ESPs are especially suited to control filterable and condensable particulate matter less than 2.5 microns. To meet the new regulations, wet ESPs need to be used downstream of wet FGD systems as a polishing device and the air quality control system. We can observe on the graph an equipment configuration that meets the PM limits in China. To conclude, incorporating the various technology elements outlined in this video has the potential to heavily reduce the emittance of particulate matter from coal-fired power plants, as depicted in the graphic. The introduced technology improvements will allow power-generating firms such as Adaro to keep using coal as a source in the future and meet the ever-toughening regulations in China and Asia as a whole. Taking Shanghai as an example, around 80% of PM is emitted from coal power plants. With our technologies, the emission rate could be reduced by approximately 70% by 2030. PM levels will then drop from 40 to 12 microgram per cubic meter. Furthermore, according to the WHO, reduction from 70 to 20 microgram per cubic meter could reduce the number of premature deaths by around 15%. Based on this, we assume that going from 40 to 12 microgram per cubic meter could decrease the number of deaths between 5 to 10%. Therefore, our new technology could prevent up to 500 premature deaths in Shanghai every year, let alone other health benefits for asthma patients and respiratory diseases.